Namaste, welcome to our YouTube channel LKG Last Night Guru, where night starts from K and K stands for knowledge. So today's topic is DFS. In earlier video, we have already covered BFS, that was breadth first search, and today we will cover the topic called as DFS. This is a depth first search. Okay, this is depth first search. See, what is the difference between BFS and DFS? See, in BFS, as I told you, we will visit all the child nodes at once, right? We will visit all the child nodes at once. For example, if 8 is having two child nodes, 0 and 4, we will visit from 8 to 0 and then from 8 to 4 at once. And then we will pop the 8 from the queue, correct? But in DFS, what we are going to do is we are going to the root. That means that we are going to the depth. From 8, if we are visiting 0 first, and then we will not come back and visit 8 to 4. We will go forward. From 8 to 0 we will go. From 0, either we can go to 1 or either we can go to 3. Correct? From 0 to 1 we will go. From 1 to 7 we will go. From 1 to 2 we will go. So we will go to the depth. So we will complete the one family first and then we will come to the another family. Right? So that is the basic difference between BFS and DFS. And in the depth first search, the data structure that we are going to use is a stack, which is nothing but last in first out, LIFO method anthrithim, right? That is last in first out. So with the help of a stack, we are going to solve this DFS, and the table will remain exactly same. Okay, so first column will be your source, adjacent vertex, visited vertex, and last one is your path, right? And even here we will get exactly 8 edges because the graph is the same as of BFS, the last example which we have solved, right? So here also the number of nodes is exactly 9, right? And the number of edges will be 8, n minus 1, that will be 8. So with the help of table we will solve this DFS. So as you can see, source, adjacent vertices, visited vertices, and then path. These are the only 4 columns that we'll get. If you want, you can add one more column, that is the data structure which we are going to use, that is stack. You can either show it manually or you can show it in the table as per your convenience, right? So now, so even in DFS, the source will not be given, but if they have given the source, consider that as your source. So for DFS, we can start from anywhere. I can start from 6, 7, 1, 0, 2, whichever node I can start. But in BFS also we took 8 as the source. So here also we will take source as 8. Okay, we will take the source as 8 and then we will start our DFS. See, source will be taken as 8. What are the adjacent vertices of 8? 0 and 4 are the adjacent vertices, right? Okay, now in visited, what we will do is we will visit only one amongst 0 or 4. Getting my point? See, in BFS what we did, the visited was 8, 0 and then 4. We visited both the nodes at once itself, correct? But here we will not do that. We will visit exactly one node at a time. Okay, see how to show that in a stack. Okay, I'll just write on the stack here. So this is how we usually represent the stack, right? Okay, so what is the source? Source is 8. It will be added into my stack, right? Now out of 0 and 4 we can visit only one vertex. For example, if I am visiting 0, right, if I am visiting 0, so this will be 8 comma 0 and path will be 8 to 0. That's it, and 0 will be added to your stack. Getting my point? So 0 will be added to your stack. Which is the top of the stack now? 0. So 0 will be your source. 4 is again yet to visit. 4 we have not yet visited now, right? So now 0 will be top of your stack. If 0 is the top of the stack, what are the adjacents to 0? 8, 1 and 3, correct? 8, 1 and 3. Obviously you cannot visit 8 because we have already visited the 8, right? Out of 1 and 3 we can visit only one node. Which node we will visit? For example, if you are visiting 1, so this will be 8, 0, 1, and the path will be from 0 to 1 and 1 will be added to your stack, right? 1 will be added to the stack. Now So 1 will be your new source. Whatever is in the top of the stack will become your next source. Very simple. Alright. Now we are coming to 1. What are the adjacents of 1? 0 and 7. 0 and 7 are the adjacents. See, we cannot visit 0 because it is already visited. So which is the only node left? That is 7. So this will be 8, 0, 1 and 7. So the path will be from 1 to 7. So what we need to do? We need to add 7 to our top of the stack. Alright. If you add 7 to the top of the stack, so 7 will become my next source. If 7 is my next source, right? If 7 is my next source, then which is the adjacent to 7? 1 and 2. 1 and 2. 1 is already visited. The only thing left is to visit with the 2. Correct? So this will be 8, 0, 1, 7, 2. And the path will be from 7 to 2. So 2 will be your top of the stack. So 2 will be again your source also. From 2 we have 7, 3 and 5. Correct? We have 7, 3 and then 5. 7 is already visited. Out of 3 and 5 we can visit only one node. Okay. If we are visiting 3, okay, then this will be 8, 0, 1, 7, 2 and then 3, and the path will be from 2 to 3. Getting my point? So 3 will be your top of the stack. Okay. Now 3 will be your top of the stack. That will be your source, and then from 3 we can visit to 4, 0 and 2. We can visit to 4, 0 and 2. See, 0 and 2 are already visited. So only option left is 4. See, we could have visited here itself. Alright, we could have visited here itself, but no, we are visiting 4 from the source 3. Correct? So this will be 8, 0, 1, 7, 2, 3, 4. Alright? So this will be 3 to 4. Right? So 4 will be at the top of the stack. Now 4 will be your source. Correct? If 4 is your source, what are the adjacent vertexes? 8 and 3. Correct? But 8 and 3 are already visited. Why you will visit again? Problem statement remains the same even if it is a BFS or a DFS. Right? We can visit one node exactly once. So we cannot visit the nodes twice. So 8 and 3 are already visited. Since 8 and 3 are already visited, this remains the same. Right? I am putting a detail here. That means that you can copy down the same thing. Right? And there is no path. From 4 we are going nowhere. See, that is when you need to pop. This is called as pop operation, and whatever we are inserting, that is called as push operation. So in data structure we will learn about push and pop. So pop means we are taking out of the stack. Alright. So 4 has been popped out. If 4 has been popped out, which is the top of the stack? Again 3 is the top of the stack. What are the adjacents to 3? 4, 0, 2. 4 is also visited, 0 is also visited, 2 is also visited. Alright, all the things are visited. Again you can copy down the same thing. Again there is no path. Whenever there is no path, you will pop it out of the stack. This also gets popped out. Now coming to 2. Correct? What are the adjacents of 2? 7, 3 and 5. 7 is visited, 3 is also visited. Right? But 5 is yet to be visited. Getting my point? 5 is yet to be visited. So here you can write 8, 0, 1, 7, 2, 3, 4, 5. So this will be 2 to 5. Getting my point? This will be 2 to 5. Okay. Now, so after popping this out, right? After popping this 4 and 3, so this also will be empty. This also will be empty. Right? I'll just rub this as of now. So which will be your top of the stack? So 5 will be your top of the stack now. Correct? So now 5 becomes your source. When 5 becomes your source, what are the adjacents to 5? 2 and 6. Out of which 2 is already visited, but the new vertex yet to be visiting is 6. Correct? So this will be 8, 0, 1, 7, 2, 3, 4, 5, 6, and then from 5 to 6. 5 to 6 will be your new source. So 6 will be added to your stack. See, now we already know that 1, 2, 3, 4, 5, 6, 7, 8. We already got 8 edges. Correct? Our answer is already there. But still, our stack is not empty. How many elements are there in the stack? 1, 2, 3, 4, 5, 6, 7. Still there are 7 elements left in the stack. Until and unless we pop all the elements out and make our stack empty, we should not stop our iterations. Even though I know that we got the answer already, but we should not stop that. Alright. Okay. So I'll carry on the next iterations. So I'll just rub this. Okay. So let us continue from here. So this is where we left, right? So 5 was the source, and then we visited from 5 to 6, and 6 was our top of the stack. Now 6 becomes our source, right? What are the adjacents to 6? Only 5 is the adjacent. Are we visiting any other new node? No. So this remains exactly same. There is no path. What we need to do when there is no path? We need to pop this out. We need to pop this out. So 6 is cancelled. Again 5 becomes our top of the stack. What are the adjacents? 2 and 6. Again this remains same because we are not visiting any of the new vertex, right? So this remains same. There is no path. Again we need to pop it out, right? Again 2 becomes your new source. What are the adjacents to 2? 3, 7 and 5 again, right? Again there is no any new vertex we are visiting. Again the path will be empty. So 2 will also be popped out. New vertex is 7. I mean the new source is 7. What are the adjacents to 7? 1 and 2, right? It is 1 and 2. No new vertex. So same thing you can copy down. No path. 7 also will be popped. Same thing. Next will be 1. What are the adjacents to 1? 0 and 7. No new vertex. This also will be empty. Again pop. New source will be 0. What is the... Okay, this is 8, 1 and... Okay, 0 is 8, 1 and 3. Correct? 8, 1 and 3. So there is nothing. There is also no new path. So 0 also will be popped. Next one is 8. Alright? Next one is 8. And what are the adjacents to 8? 0 and 4. Both of them are visited. Again, there is no path. So 8 also will be popped. Now what happens? Our stack is empty. We have popped every element, right? Our stack is empty. We call it as stack underflow. We call it as what? Stack underflow. When the stack is full, what we'll call? We'll call it as overflow. Now it is underflow. When the stack is underflow, we will stop our iterations, right? We will stop our iterations. Now, whatever the path we get, right? Whatever the path we get, so based upon that, we will draw the spanning tree. Okay. So these are the path which we got, right? So with the help of this path, we will draw the spanning tree. See, it is very easy. From 8, we are visiting to 0. From 0, we are visiting to 1. From 1, we are visiting to 7. From 7, we are visiting to 2. From 2, we are visiting to 3. And from 3, we are visiting to 4. Again, from 2, we are visiting to 5. And from 5, we are visiting to 6. What are the number of nodes that we are having? 9. Number of edges? 1, 2, 3, 4, 5, 6, 7, 8. Number of edges is 9 minus 1. That is not exactly equal to 8. And there are no cycles. That means that it is a spanning tree. So this is the answer of DFS, right? So we have two techniques, that is BFS and DFS. In BFS we use queue data structure, and in DFS we use stack data structure, right? This ends our graph traversal techniques. We have covered both BFS and DFS. I will leave the description in the description box so you can check out for that. So for more videos, follow LKG. Thanks for watching.